Good day, everyone. We are Group 1, and today we are excited to tackle our presentation, DICE Experiment Understanding Probability Distribution. So let's dive into how probabilities work with a simple die roll. Before we begin, let me introduce myself. I'm Lanz Colico, and I'm joined by my fellow presenters, Cuevas Maverick, Culilap Criselda, and Ubaldo Judel. We've worked together to bring you this insightful experiment, so let's get started. Here's what we will cover today. We will start with an introduction, then move into our methodology, followed by the execution of our experiment, analysis of the results, and finally, our conclusion to wrap it all up. So let's begin. So, our problem statement, we are investigating the probability distribution of a fair six-sided die by rolling it 100 times and recording the outcomes to see how closely they match the expected uniform distribution. Our objective is to understand the difference between experimental and theoretical probability. The task is straightforward: roll the die 100 times and record the outcomes, calculate the frequencies and probabilities, and compare them to the expected value of 1 over 6 or about 0.1667 per phase. Simple yet revealing. Before we dive into the methodology, let's clarify two concepts. Theoretical probability is what we expect mathematically for a fair six-sided die. Each phase has an equal chance, so the probability is 1 over 6 or about 0.1667, which is 16.67%. This assumes perfect conditions over infinite rows. And for experimental probability, on the other hand, comes from our actual data. It is the frequency of each phase divided by the total rolls, which is 100 per run in our case. Due to randomness, this can differ from the theoretical and especially with fewer trials. So now, Ms. Criselda D will discuss the methodology to guide us through the process.
For the methodology, this experiment aimed to simulate the random process of rolling a fair six-sided die 100 times in 3 separate runs. The following steps outline the simulation process for this experiment. The first step is to prepare materials. To begin the experiment, a standard six-sided die was selected. This die is assumed to be fair, meaning each phase 1 to 6 has an equal chance of landing face up. The second step is to conduct 100 rolls. The die was rolled a total of 100 times for each run, and each roll was done one at a time to ensure fairness. Care was taken to avoid any influence or bias in the way the die was thrown, and the surface used was flat to make sure each roll was as random as possible. The third step is to record outcomes. After each roll, the result was recorded immediately using tally marks beside the number that appeared, 1 to 6. This helped keep track of how many times each number came up. Accuracy in this step was important to avoid any miscounts or missing results. The fourth step is to count frequencies. Once all 100 rolls were finished, the tally marks were counted for each number from 1 to 6. This gave the actual number of times each phase appeared during the simulation. These counts were used to calculate the frequency of each outcome. Step 5 is to calculate the experimental probabilities. To find the experimental probability of each phase, the number of times it appeared was divided by the total number of rolls, which is 100. For example, if the number 5 came up 21 times, then its probability would be 21 divided by 100 equals to 0.21. This step showed how often each number occurred based on the actual experiment. And lastly is to compare with theoretical probability. The experimental probabilities were compared to the theoretical probability of each phase, which is 1 out of 6, or approximately 0.1667. Since a die has 6 sides and each side is equally likely to appear, this theoretical value is what to expect in an ideal case. The comparison helped identify how close the experiment came to the expected results and whether the outcomes were balanced or not. And here is the flowchart for the methodology. So, like I said, the first step is to roll a 6-sided die 100 times for each run. Second is to record each outcome. Third is to count frequency of each phase. Fourth is to compute experimental probabilities. And fifth is to compare with theoretical values.
In the first run of the experiment, we rolled a fair 6-sided die 100 times and carefully recorded each outcome. The results showed the phase 1 appeared 19 times with a probability of 0.19. Phase 2 appeared most frequently with 25 rolls and a probability of 0.25. Phase 3 came up 14 times with 0.14. Phase 4 appeared 12 times, giving 0.12. Phase 5 was rolled 21 times with a probability of 0.21. And Phase 6 appeared the least with only 9 occurrences, or 0.09. After collecting the data, we calculated the experimental probabilities by dividing each frequency by 100. Then we compared those values with the theoretical probability of 1 out of 6, or approximately 0.1667. We found that Phase 2 had a much higher experimental probability, while Phase 6 was far below the expected value. This showed that although the dice is fair, randomness can cause noticeable differences in small samples. The bar graph for the first run clearly illustrates the gap between experimental and theoretical probabilities. The theoretical value is shown as a constant line at 0.1667, while the experimental bars vary. Phases like 2 and 5 stand out above the line, while phase 6 falls significantly below it. This highlights the unpredictable nature of random events. We repeated the experiment for a second run with another 100 rolls. This time, the results were more balanced. Phase 1 appeared 20 times with a probability of 0.20. Phase 2 appeared 17 times at 0.17. Phase 3 showed up 14 times, giving 0.14. Phase 4 appeared 13 times at 0.13. Phase 5 was rolled 21 times for 0.21. And Phase 6 showed up 15 times, giving a probability of 0.15. Although variation still existed, the spread was more even. Just like before, we calculated the experimental probabilities and compared them to the theoretical probability. This time, the difference were smaller. Most phases were close to the expected value of 0.1667. The biggest deviation remained with Phase 5, but overall the results were more consistent with probability theory. In the second bar graph, you'll notice a more balanced set of results. The experimental bars are closer in height and much nearer to the theoretical line. This visual representation shows how repeating the experiment helps reduce extreme variation and produces results that better reflect expected outcomes. For the third and final run, we rolled the die 100 more times. This time, Phase 1 appeared 21 times with a probability of 0.21. Phase 2 came up 15 times at 0.15. Phase 3 showed up 16 times, giving 0.16. Phase 4 appeared 19 times at 0.19. Phase 5 was rolled 15 times for 0.15. Then Phase 6 came up 14 times, resulting in 0.14. These results were the most balanced of the 3 runs. When we calculated the experimental probabilities for this final run, we found that the values were very, very close to the theoretical probability of 0.1667. The difference were minimal and no phase showed a result that was drastically higher or lower than expected. The third bar graph shows that all 6 bars are nearly aligned with the theoretical line. The consistency in this run demonstrates how, over time and through repeated trials, experimental outcomes tend to move closer to theoretical expectations. This supports the law of large numbers and gives us a better understanding of how probability works in real-life scenarios.
Let's take a look at our results in this table. It compares the theoretical probability of a fair 6-sided die, which is 0.1667 for each face, with our experimental probabilities from 3 runs of 100 rolls each. For face 1, we got 0.19, 0.20, and 0.21 across the runs, averaging 0.20, slightly above the expected. Phase 2 varies more, from 0.25 to 0.15, averaging 0.19. Phases 3 an average 0.1467, while Phase 5 is at 0.19, and Phase 6 is the lowest at 0.1467, Notice how our totals align at 1.00, but the averages don't perfectly match the theoretical 0.1667, showing how randomness affects results with just 100 rolls per run. Now, let's analyze our dice experiment results. Based on the table, we can tell that the theoretical probability for each face is 0.1667, but our experimental probabilities range from 0.09 for Phase 6 in Run 1 to 0.25 for Phase 2 in Run 1, with averages of 0.20, 0.19, 0.1467, 0.1467, 0.19, and 0.1267, showing clear deviations. Most importantly, Phase 1 averages 0.20, while Phase 6 averages 0.1267, highlighting a trend. On the other hand, consistency. Phase 1, 0.19, 0.20, 0.21. And Phase 5, 0.21, 0.21, 0.15 are steady, but Phases 3, 4, and 6, averaging 0.1467 or lower, vary more. Now, for anomalies, key point. Phase 1 totals 60 rolls, 10 above the expected 50, while Phase 6 totals 180 rolls, 30 above the expected 150-38, 12 below 50, across all runs. These could be random, but might suggest die unfairness, though 300 rolls is a small sample.
To conclude this experiment, we roll the die 300 times to see how our results compare to what probability says should happen. Theoretically, each phase should appear about 1 out of 6 times or roughly 0.1667, but in our actual results, phases 1 and 5 showed up more often than expected while phase 6 showed up less. These differences could be due to a few things. First, 300 rolls may sound like a lot, but it's still a small sample size. Second, the die itself might not be perfectly balanced, and small imperfections can affect how it lands. And lastly, this is a good example of the law of large numbers, which says that the more trials you do, the closer your results will get to the expected average. So, this experiment reminds us that while probabilities give us an idea of what should happen, randomness can still cause streaks or surprises, especially in smaller samples. That's why considering error margins is important in any statistical analysis. Lastly, here's our pseudocode for the experiment. That's all for our experiment. Thank you for listening.